This is a short presentation I put together regarding a much longer paper which forms the bulk of the assignment. So, of recent interest is a relatively new class of high-temperature superconducting materials, which are known as quantum spin liquids. The primary interest in them is that they form one of the highest temperature superconductor categories that have been yet discovered. And from a statistical mechanics point of view, they behave as almost ideal paramagnets. A subclass of quantum spin liquids is known as Kitaev quantum spin liquids, which form formed from a two-dimensional sheet of primarily D-block halogenides and oxides. In particularly, the two most widely studied are ruthenium chloride and dilithium iridium oxide, Li2IR03. We'll be talking about ruthenium trichloride. Yep. And already talked over the second slide. And the third slide. So the equations of interest. One problem with the current and previous published research on ruthenium chloride is that previous research has been calculated using the Ising model of paramagnets and mean field theory of balancing the influence of the charge, which has one problem in that the influences between the individual spins of the ensemble of the atoms are not equally distributed. And this middle equation here is mostly just to show the complexity. It is one of the best available published mathematical models for experimentally derived data, but it still is struggles with predicting all of the experimentally derived data accurately. So the two important factors that we need to know from this are the beta and gamma factors, which correspond to the influence of the part of the nearest neighbors of the calculated spin for this equation. So some equations of note, which also include why the other ones were mentioned in that last slide.
Stephen, let's maybe slow down a little and on previous slide.
Right. So starting from the top, we have the partition function z and the general Ising model of a paramagnet Hamiltonian function, which we can use to calculate the average energy of an ensemble as the partial derivative of the ln of z over the derivative of the thermodynamic beta, which is of importance because since this is a paramagnet, this is where the next slide comes in, we can act as though the individual spins energy are either plus or minus mu h for an external magnetic field of strength h and chemical potential mu, which we make that assumption to be able to use the following formula. M equals partial derivative of the Helmholtz free energy over the strength of the magnetic field, which can also be calculated as n number of particles is equal, or n number of particles times tan h of.
Stephen, let's slow down and go back to the previous slide.
Yes, again.
So,
what part?
How does the energy of individual spin that appears as a first equation on the next slide connects to anything on this slide?
Right. So the average energy can also be calculated as the summation of the probability of a state times the energy of that state.
Can you show it? Do you have the laser
Yeah.
point? Okay. Okay.
How does it? So save it.
Like in previous slide, second equation.
Yes, that was a general model equation for an Ising calculation.
So what is
Right. Oh wait.
H sub j in this?
So that calculates is that it's J sub I is the strength of the interaction on is the calculation for the Hamiltonian energy of equation of point I in a lattice work where J sub I is the influence from the nearest neighbors of other spins in the lattice, with the sigma equaling the spin energy of that.
What sigma? What is sigma?
Sigma is the spin and energy of a single spin, either I or J, as I with J being the nearest neighboring spin.
Okay, so lowercase.
So that general one calculates only 2. For each additional one, you need to add that factor again.
Okay, so lowercase I and j are indices of the sites.
Yes.
And a diagram, well, maybe there is no time for you to update your proposal, but when showing equation, it would be much better to show a little diagram with lattice and showing site I, site j, something like this.
Right.
And now, what is sigma? Sigma sub I?
That is the actually still one. So I have a note written about it specifically. My understanding is that the sigma sub I and sigma sub j represent the energies of the spins respectively.
It is it sounds very strange. It means that energy is like Hamiltonian, total energy is proportional to energy squared. If you have product of two, letter sigma corresponds to Latin letter S, and likely it corresponds to spin operator. Spin projection, spin operator, not the energy.
Right.
So okay, and J is the spin-spin interaction energy. Sigma sub I, sigma sub J is spin operator. Then what is H lowercase sub J lowercase?
H lowercase j and the second half, the mu sum H sub j is the strength of the magnetic field at site J.
So what is magnetic field, mu or H sub J?
In this one, mu is not magnetic field.
So mu is like dipole or interaction constant, right?
Yeah.
Okay.
That's my
H sub j shows that magnetic field is inhomogeneous and it is different at different spatial points. If it would be homogeneous, then what one would remove the index j and would make it just a constant out of brackets?
Yes, I believe this is, again, a generalized equation, and so it is to account for if it is not equal, but if it is equal, then yes, it would be a constant that would cancel.
Okay, and this lowercase mu times h lowercase sub j times sigma sub j would define contribution of individual spin to magnetic field interaction to the total Hamiltonian. So if the spin-spin interactions are absent and there is only one spin, then this would reduce to plus mu h or minus mu h.
Yes.
Okay, now let's go to the next slide and make sure that you understand it correctly.
So on this slide, H is magnetic field strength, and mu is chemical potential.
And how does mu on this slide and h on this slide agrees or differs from mu and h on the previous slide?
This is which h?
Lowercase h in the second formula.
Lowercase h sub j would be equal to uppercase h on this slide.
Then why you are using different symbols for the same thing? I'm not trying to give a hard time. I'm just trying to help.
On the paper that this equations on this slide were taken from the paper I wrote with this. This one with h sub j was not, and I did not have time to correct it.
Okay, then one can add declaration. In what follows, h lowercase is equal h uppercase, instead of correcting it everywhere. Okay.
But the important part is that through this, we can calculate some important thermodynamic quantities with this assumption, and that is that since the magnetic moment is also equal to the negative internal energy over the strength of the magnetic field.
So F is internal energy here. Yes, no?
F is the Helmholtz free energy.
Okay.
And negative U is the negative internal energy.
And what is the goal? Why this sequence of equations is presented?
It's going to get to that at the bottom. So,
but let's declare the goal, and then with this motivation, try to.
The goal is that the script F of TCU over TCR is the frustration factor of the magnetization, which for an ideal antiferromagnet, script F would be equal to 1, and for a quantum spin liquid, F would diverge to infinity, as if an ideal quantum spin liquid is a permanent ferromagnet, and thus its critical temperature for paramagnetism and ferromagnetism is 0 Kelvin.
Mm-hmm.
So this would allow us to calculate sort of how close any hypothesized material that we're working with is to an idealized quantum spin liquid, and thus its potential eventually as a high temperature superconductor.
So you're going to screen through several candidate materials, and with some methodology evaluate this fraction F, and the material that will give F close to infinity will be your best candidate.
Yes.
Okay.
Previous published papers have included statements that an F value of larger than 100 is a very good candidate as a quantum spin liquid.
Okay. And now and now let's go through equations after this motivation.
All right. So from the magnetic moment, we can calculate the magnetic susceptibility chi, which didn't show up as a fancy character on this, which is the magnetic moment over the strength of the magnetic field, which we already know, and chi also being equal to an internal Curie constant, capital C, over the temperature minus TCU, and our critical temperature is equal to TCR is equal to K, the Boltzmann constant, times the this is interesting, times the critical temperature divided by J, where in this case J is the J sub I, is my understanding.
J sub I comma J, right? This
yes.
Capital J has two indices. Okay.
Right. There's supposed to be commas there, they didn't show up.
So it is a spin-spin interaction.
My understanding, yes.
Okay. And this critical is
the critical temperature at which it has a phase transformation and is no longer a boundary between paramagnetism and ferromagnetism.
I have a silly question. Maybe I misunderstand something, or maybe it is a typo. If in the third from the bottom line, I apologize, I may look very silly, but is it possible to cancel T sub CR on left and right?
Mm-hmm.
It is written T sub CR equals K times T sub CR divided by J. It looks like it not.
I didn't have the time to put this, but this has actually been solved analytically for a case of a two-dimensional lattice of spins without a magnetic field, and in that case, TCR is actually a constant.
But how to find it? Because in this equation, it doesn't. How one can solve for TCR? Is there any typo in equation? Is maybe on left and right? It depends on. It is evaluated at different conditions.
Yeah, there might be. I wrote this slide rather fast as I was in between helping students during office hours. So there might be a mistake on my part, but TCR has been found for materials, so it is possible to find it.
If time allows, please check it before submitting your proposal. And David suggests that it could be two different T sub CR on left and right.
Right.
Removing equations is not a good impression in your proposal, but putting some equation with typo error could be provocative. So better double check.
Right. If you have any concerns, I believe I shared the paper itself with you, Dr. Killen, and I will be taking advice on it until about 11 o'clock tonight.
Okay.
Right. So there have been a number of proposed and published papers that have given different values to the two factors I mentioned earlier, beta and gamma, as well as I mentioned earlier, deviations from the ideal quantum spin liquid state by actual samples of ruthenium chloride due to the fact that its structure is not perfectly symmetrical in all directions. This has led to a wide variance of important data, in particular the critical temperature at which it stops behaving as a superconductor, which is the reason for all of the equations, is to try and computationally compute that, hopefully to greater accuracy by the original proposition was to use, so I'll get to the next slide actually. The proposal was that graphene is a perfect honeycomb structure, and one of the uniting factors of quantum spin liquids of this category is that they all have a hexagonal honeycomb structure similar to graphene. And I'd like to thank Dr. Gillen for providing these wonderful graphics. The initial idea was that by layering a single molecular unit or so thick layer of alpha state ruthenium chloride onto a layer of graphene, that the electronic interactions between them would hopefully sort of stretch or compress the structure of the ruthenium chloride to a small amount that would allow for a greater accuracy in determining the importance of those two factors. And that is the final idea.
Oh, no. Let's keep discussing. Oh. Let's keep discussing. You just started it. There is, I'm expecting a lot more explanation of this.
Professor, my class is starting.
Okay. Then if your class is starting, you may leave, but we will discuss here because it's really interesting subject, and I think the key part of your proposal starts here. Okay. Yeah, I hope recordings will go well and you will watch and.
No, it won't be. The grade is on the paper.
Mm-hmm.
So, but thank you for your time, everyone.
Oh, yep. Thank you. Thank you, Stephen, for sharing this interesting thing. And if it is okay with everyone, I would like to continue his subject. Just, it's not our main goal for the group, but it could be a possible initiative for the future if one day we finish all. Stop sharing. So, in case we are done with all the projects and we need some inspiration for the future, it could be an interesting thing to try. And here is a model that Stephen just started. And one of the aspects in such models is to assess the parameter J that Stephen was introducing, the spin-spin interaction. So basically, if there are, I need to step back and just say a couple of words. Maybe we do share in a different form and make So why ruthenium chloride is important? So it is 1 ruthenium 3 plus, and it is connected to 6 chlorines in a semi-planar way, in such a way that the balance, stoichiometric balance, is 3:1. So in some sense, one is looking for unit like this as a elementary unit, or maybe duplication of this as an elementary unit, and then the remaining chlorines are coming from the periodic image. So the ruthenium, the chlorines come into octahedral form with 3 plus should have 5d electrons, right? If we look into the periodic table, and in the octahedral arrangement, this 2, 3, the electrons are coming to the low spin configuration because of the octahedral splitting is quite big. And this configuration has 1 unpaired spin, which is a cool object to study. So basically, it's 2-dimensional lattice of sites that do have 1 unpaired spin. And these spins, when there is 1 spin per ruthenium atom, 1 unpaired spin per ruthenium atom, they have different configurations. When all of them are oriented up, all of them are subsequently oriented in the alternating order, up and down, up and down. And there could be some other exotic configurations. So, of course, it needs either spin polarized or non-collinear calculations. And the arrangement when all spins are up is called ferromagnetic, and when all spins are alternating is called antiferromagnetic. AFM. So the minimal and standard task in the community is to compare the total energies of these ferromagnetic and antiferromagnetic combinations, and out of subtraction of this thing, one can get the J sub ij that Stephen was introducing. So Ji sub j, it is the strength of interaction between spins or coalesced on different neighboring sites. So I lowercase I lowercase j are nearest ruthenium. And by monitoring different geometry of these models, by presence or absence of graphene substrate, by allowing or not allowing it to optimize, maybe by doping, by different, adding temperature through molecular dynamics, one can explore different regimes of this model and explore this spin-spin interaction parameter. So maybe Stephen has in mind different things. Maybe he read some more advanced thing, but it could be a first step in making this project for the research. So preparing different spin configurations by practicing the n up down keyword, exploring total energy in different configurations and subtracting them from each other. So it is a minimalistic thing that could be helpful in practical addressing of these exciting subjects that Stephen was exploring. In addition, one can plot spin polarization, which would be total spin alpha component at each point of space minus total spin beta component in all points of space. So this spin polarization for different spin up and down parameters is shown, and there are some interesting observations. Before we go to this practical things, the energy of this subtraction should be compared to room temperature or evaluated in temperature units. So if spin-spin interaction is bigger than room temperature, then magnetic properties and these exotic things will be observed at room temperature. If it is really small, then one needs to cool down this this model. So here is the slide that Stephen was showing, and the stuff displayed in these diagrams is subtraction spin polarization parameter as function of space. So it is negligibly small thing. It's just exaggerated, but basically it's very close to zero for the requested antiferromagnetic with n up down equals zero. It means that through DFT self-consistent procedure, spins will be arranged to compensate each other and basically to alternate. This is maybe not matching expectations. Let me go to spin. Yes, antiferromagnetic. So in this simulation cell, there are total 8 ruthenia, and if one mandates the n up down equal 8, which means that all spins at all ruthenium ions are oriented collinearly. And one may want to compare total energy under this constraint and total energy when they are all alternating. In addition, one can select a configuration 1, 2, 3, 4, 5, 6, 7, 8. In addition, one can select a configuration when all except 2 spins are oriented collinearly. So if one flips one spin, then it creates one compensated pair, and total number of unpaired spins will be 6. And here is the situation when there are 6 points where spins are unpaired, and there are 2 where they are paired. And there is a little table summarizing these energies, and in the units of new electron volts and temperature. So the lowest energy when it is magnetically ordered, in this specific case, when it is all parallel, anti-ferromagnetic, and one can use it as a starting point. Then when they all are alternating, it is about 0.1 electron volt, which is bigger than room temperature. And if only one pair is has compensated spins, which means first excitation on the basis of antiferromagnetic simulation, then the energy is smaller than room temperature, which is interesting observation, and which this energy of about 20 millielectron volt can be related to the spin-spin interaction parameter that proposal offered by Steven needs for evaluating some additional properties. So I believe I'm done with this little demonstration, and I can serve as a representative of Steven and maybe try to accept any questions to him and forward them to him. Or if questions or expressions of lack of logic, because I think it is the main question to his proposal.
I guess my question is just kind of more broadly, what does spin have to do with superconductivity? Because normally I think conductivity, you think charge.
I admit this question to be transferred to Steven. It's not my area of expertise, and I will not give the full answer. But indeed, there are records that these materials are candidates to be simultaneously magnetic and superconductors. And a little piece of understanding from myself is as follows. For regular superconductors, the mechanism for having zero energy of excitation for charge carriers is formation of pairs of electrons. And when electrons are paired together, the spin from fractional, from 1/2 of this quasi-particle of paired electrons combined together becomes zero, or if they're anti-parallel, or one if by some way they are parallel. And if it is integer spin, then the particle becomes boson and obey Bose-Einstein statistics, which means one can fit as many such quasi-particles at certain energy level as is available as one wants. So it is drastically different from Fermi weight that we all are practicing, from Fermi distribution, from our Bow principle, when each level can hold only one state if we take into account spin, or two states if spin is left behind. So if we fight successfully these spin restrictions, it means this paired spin, one can put as many as needed paired spins into one quantum state, lowest state, and it will be very low, negligible energy to excite infinite number of these paired spins to the next available level. So the current in response to applied voltage will grow dramatically without any constraints. One will deal not with one pair of quantum levels, but with two infinities. Infinity of like Homo and Luma in the system will hold a large number with infinite degeneracy. And it was a general statement. And for the system of interest for Stephen, there are configurations when spins are paired, especially when we go from totally ferromagnetic to one, just flipping one spin and forming one anti-parallel pair. So such state is not a fermion anymore, it is a boson. And out of such states, one hypothetically should be able to create superconducting state, superconducting phase. But I may have already done some substantial errors in this story. It's, we are on the equal foot entering the foreign territory.
Mm-hmm.
I was kind of impressed by looking on these things and was remembering the work that Yvonne was relatively recently doing, and before it was done by Hugo for spin flip excitations in lanthanides. So there, the lowest excited state is just making one spin flip without spin orbit interaction, just in spin polarized language, just changing the constraint for magnetization, and up down will give the lowest excitation. In some sense, it has some similarities. So by flipping one spin, one goes to the next excited state. Any and the question from Aaron was very natural. When Stephen presented it first time 2 weeks ago, I wanted to ask this question, but was hesitant.
Yeah, because it uses a lot of familiar words, just not in the context I'm used to, like a spin liquid.
Mm-hmm.
Usually, well, if I think of that, that's like paramagnetism.
Mm-hmm.
And then the quantum part, it's like spin's already quantum, so it's just from the naming, it's kind of hard to understand the topic as a whole.
This, I have a couple of additional comments. This is not quantum or computational problem. This is more statistical mechanics problem. So to predict realistic experiment, one needs to do average over multiple configurations, and the apparatus of statistical sum that Stephen is offering. And I think it was natural because he's making it as an exam on thermodynamics. So this statistical sum language is most appropriate. Another thing that DFT can be doubtful to use in this situation. Maybe it is useful, but under question, because it is multiple electrons, multiple electronic configurations. So DFT is a single configuration theory, and here when approaching the area where there are several configurations close to the energy, and there could be superpositions between them. So configuration interaction could be more appropriate for spin enabled couple clusters, which would of course reduce size of the system. So this in physics, they call it collective excitations and collective phenomena, when a lot of quantum particles form quantum states through interaction with each other. And another comment, to my understanding, Stephen is considering how all these advanced properties, which are cool and challenging to describe already, how do they depend on the composition of the model and its configuration in sense of how it is assembled, what are the sizes, what is the substrate. So his main point is that by making a constraint to periodicity, by squeezing or contracting this lattice, one can drastically modify its electronic state and facilitate or suppress quantum properties of interest. So how I understand what he was telling, that if one removes graphene substrate, if one lets this quasi two-dimensional ruthenium chloride model to optimize as it wants, then interesting quantum states will be suppressed. And if one slightly expands it by depositing on the graphene and making like a template for periodicity, something good is happening. And from this point of view, if it would be a real proposal to submit to agency or to try to convert it into a paper, it would be compare results with and without substrate as a simplest numerical experiment. Okay. Any other points of curiosity or complaints about weak sides of this model or presentation or ideas or logic or connection?
I guess, do they make them with other halides? Because then that would be a way to tune the ruthenium distance.
Exactly. And this is unfortunately, this is already published. Like no graphene substrate, only the plain material, and then exploring this anti-ferromagnetic configurations with different halides and looking for getting this exotic states as a function of chemical composition. Yes, very, very natural train of thought.